G'day, this should be the final video of the series on PB2, multi-stage events and applications of probability. Today we'll add one final tool to the box, the tool of expectation, including the application of expectation to financial situations, also known as financial expectation. The theoretical probability is what should happen in an ideal world, whereas the expected outcome is what is expected based on the theoretical probability. That is, if we toss a coin 100 times, as each outcome is equally likely, we expect there to be 50 heads and 50 tails. If we roll a dice 180 times, we expect there to be 30 of each number. The expected outcome is the number of times we expect a particular outcome to occur in a certain number of trials. Put another way, if the probability of an event is P and there are n trials, then the expected number of times the event will occur will be given by P multiplied by n. If a dice is rolled 120 times, how many sixes would you expect to occur in 120 rolls of the dice? The probability of a 6 is equal to 1/6, so therefore the expected number of sixes is 1/6 times 120, which is equal to 20. Another example, if 1 in 6 paddle pops win a free paddle pop, and I buy 24 paddle pops, how many free ones should I expect? The probability of a free paddle pop is equal to 1 in 6. The expected number of free paddle pops will be given by 1/6 multiplied by 24, which means that I can expect 4 free paddle pops if I've bought 24. The financial expectation combines the probability of an event with the associated costs. It is a concept widely applied in companies and business, but all games of chance also consider the financial expectation. The financial expectation of a game of chance is the average amount of money returned per game. It is calculated by multiplying each financial outcome by its probability and adding the results together. Here's an example from David Cobb, a teacher from Scone High School who had prepared the same example from New Century Maths Year 12 General 2 textbook that I was going to use, so I thought I'd give you a break from my voice.
Okay guys, so we're doing a financial expectation problem. You find the probability, you times it by the outcome, and then you add up all your outcomes. So, Xanthi plays a game involving the tossing of 2 coins. She wins $5 for 2 heads, $1 for a head and tail, and 0 for 2 tails. What is Xanthi's financial expectation from the game? Alright, so the first thing that we need to do is we need to get our sample space organised. We could draw a table where you show the heads or tails, heads and tails. So you'd have heads, 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 tails, tails, heads, tails, tails. And that would be the 4 different outcomes. So, what is Xanthi's financial expectation for the game? So, she could either get double tails, a mix of heads, tails, which we will say is the same as tails, heads, or she could get heads, heads. Now, what we need to do is work out the probabilities for each of these. So the probability of double tails, well, as you can see, going back to our table here, double tails, that happens 1 in 4 times. When it comes to a mixed, you can get a tails head or a head tails, which doubles the chances of that occurring. That's going to be 2 over 4 or just 1 out of 2. So half the time you'll get a mix. And for heads, heads, the remaining probabilities are 1/4. Now to find the financial expectation, what we do is we get the probabilities and we multiply them by their outcome. So I might just write here, draw an arrow, if she wins $5 for 2 heads, so I'll just put down here $5. $5. For this one, actually I'll keep reading, $1 for a head and a tail, so that's $1, and $0 for tails. the way we work out the financial expectation is we go 1/4 times 0, which of course is going to be 0, plus 1/2 times 1, plus 1/4 times 5. So 1/4 of the time she gets nothing, so that's still nothing. Get our calculators out, we go 1/2 times 1, so that's going to be 50 cents. And we add to that 1/4 of the time, she'll get $5. So 1/4 times $5. Now my calculator, that's 7/4. So obviously that's not what I want, because I want my answer to be in dollars and cents. 1.75 is a better answer. $1.75 is the correct answer. So I hope that clears that up.
Thanks for that, David. Let's have a look at another example. This example is based on a game with 2 dice. George rolled a pair of dice in a game of chance that costs $1 per roll. The table below lists the financial outcomes for each event. So we can see from the table that if you roll a double, that is both dice the same, you win $2. If you get a sum of 7, you win $3. If you get an odd sum but not 7, you get $1, that is you get your money back. And if you get an even sum, except for a double, you lose $1, that is you don't get anything. Calculate the financial expectation for this game is part A, and part B, on average, will George make a profit or loss? To answer this question, we first need to consider how many outcomes there are. The easiest way to do this is to think about a table. If we have dice 1 on one part of the table and dice 2 on the other part of the table, we can see that dice 1 has numbers 1 to 6, dice 2 has numbers 1 to 6, and if we add all of those numbers into the table, we get the following. Let's look then at the probability of each of the events for this game. The first event is a double. The probability of a double, we can see there are 6 doubles out of a possible 36 outcomes, and so therefore the probability of a double is 6 out of 36, which is equal to 1/6. The probability of a sum of 7, we can see that there are 6 ways to get a sum of 7 out of 36 possible outcomes, giving us also 6 out of 36, which is equal to 1/6. The probability of it being an odd sum, except for 7, all the odd numbers we can see here, except for the 7s, there are 12 of them. So that means that the probability of getting an odd sum, except for 7, is 12 out of 36, which is 1/3. And the probability of getting an even sum, except a double, again, there are 12 numbers other than the doubles, so that means that the probability of getting an even sum, except for a double, is 12 out of 36, which is also 1/3. Calculating then the financial expectation, we've multiplied the probability of each event with its associated cost, and then we add those together. That means that we've got $2 multiplied by 1/6, $3 multiplied by 1/6, plus $1 multiplied by 1/3, plus -$1 multiplied by 1/3, because to lose $1, that is minus $1. Putting that into our calculator, we obtain the answer of 0.83 repeater. Rounded off gives us the answer of $0.83 or 83 cents. Part B asks, on average, do you think George will make a profit or loss? Part A told us that on average George would expect to win 83 cents per game. But looking back at the scenario, we see that it costs $1 to participate in each game. On average, George is winning less than it is costing him to play, so he should expect to make a loss if he continues to play the game. All the best.